Right, so Fleming's left-hand rule. This is higher tier only. It's not on the foundation paper. It is the idea that when you have a conductor carrying a wire in a magnetic field, it will experience a force. Previously, we said that when you've got current flowing through a wire, it experiences a magnetic field around the wire. Well, if that magnetic field is in another magnetic field, those fields, just like magnets, we're going to repel each other or attract. They're going to move relative to each other. And this effect is called the motor effect, right? Now, if we can figure out the magnitude of the force, because if the conductor is at right angles to the magnetic field, then that means the value of the force measured in newtons is going to be the magnetic flux density of the magnet, which is measured in Teslas, times by the current traveling through the wire, times by the length in meters of the wire in the field. And that tells us how strong this force is on the current carrying wire or on the magnet. It's Newton's third law, so they're kind of going to repel each other. Now, the direction that this force is going to move in is Fleming's left-hand rule. Now, Fleming's left-hand rule, I often think you kind of put your finger in this gum position and also stick your middle finger out like that. It has to be your left hand. The thumb shows you the motion, the direction of the force. First finger field, second finger current. So I often think of it as that, thumb motion. However, I know other people sometimes find it easier to think of it instead as FBI, first finger force. Thumb is the force, the first finger is the magnetic field, so B, and the second finger is the current. It's up to you however you want to remember it. Now, we have to remember that fields always go from north to south, they're due south, and current always goes from positive to negative because it's opposite to the way you think an electron would go. So if I've got this wire here in this magnetic field and I draw my field lines on, they're going to be due south. This is a uniform magnetic field. My first finger lines up with the field, so it goes down. My second finger lines up with the current, so it's going that way. And then my thumb, you can't see it, but my thumb is pointing down into the page. So this wire is going to move down, or sort of like away from your screen. It's going to move into the page. Now, if we were to reverse the field like that, it would move up. If we were to have it like this and we were to reverse the current, it would move up, right? So reversing one of those things, and obviously the increasing it would be increasing the magnetic field strength, increasing the current, or increasing the length. Works best when they are perpendicular to each other, so when there's a right angle there. Otherwise, it's not as strong if they're not at a right angle, and this equation doesn't apply. That's it.